Welcome to the Foundry by Forge College. I'm your host, and in today's explainer, we're looking at the engineering behind your smart contracts. Specifically, we're going to show you how to save some serious gas money through optimized state reading. Let's just jump right into it.
Okay, let's look at the blueprint for today. We'll be covering 1. The cost of reading, 2. Navigating nested mappings, 3. Selective and packed getters, 4. Cold versus warm reads, and 5. The optimization blueprint.
So, Section 1. The cost of reading, or why exactly is hauling data so expensive? In our previous lesson, Testing on DevNet, Practical Steps, we did some really great work fixing buggy writes and storage mutability issues. But, correcting the write side is really only half the battle. Now we actually need to tackle those clunky, expensive reads. I want you to think about your smart contract like a high-performance hypercar. Now imagine that hypercar hitting a ridiculously expensive toll booth every single time the driver just wants to check the speedometer. It's absurd, right? But that is exactly what happens when you have unoptimized state retrieval on the EVM.
Or, think of it like a filing cabinet. Retrieving a naive, full struct when you only need one single Boolean variable, it's literally like hauling a massive, 4-drawer steel filing cabinet all the way to your desk just to read one tiny sticky note inside. It's just incredibly inefficient. What we really want here is selective data fetching. We just want to grab the sticky note. Which brings us to Section 2, Navigating Nested Mappings and Mapping Out Our Blueprint.
To actually fix this heavy hauling problem, we first need to look at our data structures. So we frequently use nested mappings, right? This is where a mapping's value is another mapping, like, say, an account ID pointing to specific data keys. And don't get me wrong, they are fantastic for organizing state, but they can also create these deep, incredibly expensive paths to retrieve that data if we aren't, highly precise with our state management.
Now, what's really interesting about this slide is the layout of the user data struct we've sketched out here. Look at how it packs its primitive fields right at the top. The integers and flags just sit neatly together. But then, right below them, we have the larger owner address, which causes padding. And finally, a dynamic metadata string stored in a completely separate slot. Grabbing this entire struct every single time? Yeah, that's exactly what's draining your gas. All right, Section 3, Selective and Packed Getters. Extracting exactly what you need.
So how do we actually fix this? Well, we have 3 primary techniques in our engineering toolkit today. First, selective getters. Second, precomputing or caching aggregates. And actually, just a quick aside on caching derived booleans, like an active status. It really only makes sense to cache these if your reads dramatically outnumber your writes. Keep that in mind. And third, packed getters.
The absolutely crucial point here is that selective getters are our primary weapon against that filing cabinet problem we talked about. By designing view functions that return only the specific primitive fields we ask for, we leave all those heavy, dynamic strings safely behind in storage, right where they belong. Taking it a step further, though, we have packed getters. This is just a brilliant technique. We use bitwise operations to squeeze our small flags, balances, and timestamps into one single 32-byte word. We are literally bundling multiple fields into a single compact snapshot. And doing that saves the EVM from having to perform multiple storage reads. It's a huge win. Now, I should clarify something vital about the environment you're actually querying from. If you're doing an off-chain query from a front end using an eth_call, pulling that whole struct is basically free and fast. But if you are executing these reads on-chain during a smart contract transaction, you are burning real EVM gas. So our optimizations here, they are absolutely mandatory for those on-chain calls.
Moving on to Section 4, Cold versus Warm Reads, Starting the Engine.
To validate these solutions, we really have to understand the difference between a cold read and a warm read. A cold read is that first execution after deployment. Honestly, it's kind of like trying to start a 20-year-old car in the middle of a freezing winter. It takes a lot of juice. A warm read, on the other hand, is for repeated calls where we benefit from EVM caching. The engine is already purring, so it's so much cheaper.
And this brilliantly illustrates just how massive the impact of these optimizations is. Look at this. We dropped from a painful 45,000 gas for a naive struct cold read all the way down to just 15,100 gas using a packed getter. That's huge. And even the warm read drops from 32,000 down to roughly 9,200. That is just an incredible savings.
Because of this, I want you to set a milestone goal for yourself. Aim for at least a 10% gas reduction for your on-chain calls. Seriously, if you aren't hitting this 10% threshold when refactoring, you really need to double-check your code. You are probably accidentally copying dynamic strings into memory without even realizing it.
Which brings us to Section 5,
The optimization blueprint, or rules for the road.
Listen, if you write down just one thing from this explainer, let it be the golden rule of efficient state retrieval. Prefer returning primitive fields rather than whole dynamic structs. That's it. It is the overarching principle that guides absolutely everything we've talked about today.
So let's summarize our blueprint really quickly. Return only the required primitives. Avoid those large dynamic fields. Pack your small fields into tuples or a bytes 32 snapshot. Always measure your cold versus warm gas to actually prove your optimization. And finally, document your API so your retrieval module is clean and easy for the next developer to integrate.
Now, I'm going to leave you with a bit of a provocative thought to chew on. How exactly will your beautifully optimized retrieval blueprint perform when it's suddenly combined with heavy, complex transaction logic? Well, we're going to synthesize exactly that in our next explainer. By the way, students in Forge College's advanced learning courses use these exact blueprints before moving to production. Make sure to visit forge.college to learn more and dive deep into this and other Web3 topics. Until next time.